Hey guys, it's Korma IB and we'll be looking at Gaussian elimination, which is an effective tool to solve systems of linear equations with three variables in this video. This is an extremely common question to come up in the IB, but it will have practical applications in year 13 or the second year of IB, me being from the UK, we just refer to it as year 13. But we'll be looking at equations slash intersections of planes in a 3D space. However, that comes under vectors. Uh, Gaussian elimination does come under functions 1. So in this video, we're going to be looking at systems of linear equations, row operations, solving 2 by 2 systems of linear equations, and then 3 by 3 systems of linear equations, which is much more likely to come up in exams. They typically come up in the format of 3 by 3. But first, we're going to be tackling 2 by 2 and getting familiar with the row operations. And yeah, let's get into it. So what I like to do with the Gaussian elimination is that there's three simple steps that we have to follow in order to attack a system of equations using Gaussian elimination. So the first step, when we have a system of equations, is to convert the system into augmented matrix form. Okay, so say that we have a system of linear equations, 2x minus y plus z to minus 1. X, let's just say 0, y minus 3, z is equal to 4, minus x plus 2y minus z is equal to 0. So when we're converting a system of linear equations, such as this, into augmented matrix form, what we do first off is all these equal signs you see here, we replace it with just one single vertical line, like so. Next, what we do, we only include the coefficients of each equation. So let's look at this row, for example, row 1. To write this in augmented matrix form, we would simply write 2 minus 1 plus 1. And then the solution would be minus 1. This plus shouldn't be here. Basically, we don't write any plus signs. We just assume the number is positive, if there is no sign before it. But if there's a negative sign, obviously that's denoting that it's a negative number. If you're unsure where I got these values from, literally coefficients of each variable in the equation. It's important that we maintain this order with it going horizontally, and we keep each equation to itself, whereby we can see that this is obviously equation 1 or row 1, as we refer to when we're looking at a matrix of equations or system of linear equations. So let's look at the second row. This would simply just be 1, 0, minus 3, and then 4 as the solution to that equation. We have minus 1, 2, minus 1, and 0. Now, this is step 1. This is step 1. This seems easy enough. Obviously, we're literally just writing down the coefficients of the equations and converting it into a form. The reason we do this is that it's much easier to see what we're doing and manipulate this system of linear equations to actually obtain our solutions. But how do we actually manipulate this system of linear equations? Well, this leads me on to step 2. Let's write step 2 here. Step 2, which is these principles can be also applied to augmented matrices as row operations. So step 2 would be row operations. This, to summarize, is literally just a method in which we are able to manipulate the rows in order to find a solution by cancelling out different coefficients to find an equal, such as like to find a solution set basically. So I will walk you through this. So row operations that are valid. So this is what you can do using row operations. So you can interchange row. You can replace any row with a non-zero multiple of itself. self, and you can replace any row by itself plus a multiple. It's important to understand that all of these operations, they are all valid. Okay, so if you are using row operations, they have to be under one of these subheadings, otherwise it will be invalid. And the reason for this is row operations do not change the solution to the systems. So to the system. So row operations do not. Kind of regret writing capitals now, taking a bit long, but where we are, the solution of the system. Bloody hell. Alright, so now I'm going to show you examples of how we can use each of these different subtopics of like interchanging rows, replacing any row. I'll show you how we can do that. So I'm going to show you an example of each one. So let's say we have an example system. We'll just do 2 by 2 for now. So we'll have, let's just say we have 2x plus y to minus 1, x minus 3y is equal to 17. Now, of course, step 1, change to augmented matrix form, sorry. So obviously, vertical line here, coefficients only, 2, 1, then the solution to that equation, minus 1. We have x, 1, the coefficient before is 1, and then we have minus 3, and 17, denoting minus 3 and minus 1 with a negative sign at the start, because obviously they're negative. So let's say we were to interchange rows 1 and 2, which basically just means swapping them around. So to interchange rows, to interchange rows, rows, so e.g. 1 and 2. So firstly, we need to label our rows. Typically, we do it from the top down, so this would be row 1. Row 1 literally just stands for equation 1, and then we have row 2. So to interchange rows 1 and 2, so let's just say, so we would have 2, 1, minus 1, 1, 3, 17. Then we would write this symbol, which literally just means has the same solution as. And then we would switch the rows, which will perform the operation, which literally we're just switching the rows. So if you can't see what I've done there, I've literally just made row 2 the new row 1, and then row 1 the new row 2. So I've just changed their position. So now row 2 becomes row 1. And how we would demonstrate this or show this is by saying R1, then we do a double-headed arrow. It's very important you do double-headed because this shows that they're switching position. So this indicates row 1 and 2 have been interchanged. So if we multiply, so let's say we're multiplying row 1 by negative 3, for example. So let's write our augmented matrix one more time. So our augmented matrix is 2, 1, minus 1, 1, minus 3, 17. So again, labeling our rows. So row 1, row 2. Once you do get better and more comfortable with this, you don't have to do all of this labeling. You would simply just perform the operation. So if we're multiplying row 1 by negative 3, so we would write our augmented matrix 1, 17. Symbol to show that they have the same solution. Multiplying row 1 by minus 3. So we're literally just multiplying all these coefficients here off row 1 by minus 3. So minus 3 times 2, minus 6, minus 3 times by 1, minus 3. Then we have positive 3 on the end here. And then at the bottom, because we've done nothing to row 2, we just write 1 minus 3 and then just 17. So to denote this, we'll just show minus 3 R1 becomes R1. So what this means is that it's literally what we just done. It just shows that, sorry about that, it shows that row 1 has been replaced by minus 3 times by row 1, which is literally what we've done here. It's important to know that these do have the same solution. You may think that multiplying by negative 3 might change the scale of the equation. You might be right, but the solution set still stays the same. Because as we know, we've scaled the entirety of this equation. Even the solution has been hit with a scale of negative 3, I mean. So it doesn't change anything except for the coefficients and yeah. So moving on now. Let's just say we replaced row 2 by twice row 2 minus row 1. So let's just say, we'll write down our augmented matrix one more time. 1 minus 3, this one, 17. And then we'll say has the same solution set as 2, 1, 1, 0, 7, 35. This is what you should get. I'll show you how I got to this answer. So guys, don't be scared to show you're working out on the side, even if you're doing a simple subtraction. So what we do here, so I have augmented matrix here. So what row are we looking at? Row 2. Which one's row 2? This one. This is row 2. So we're doing twice row 2 minus row 1. So what are we doing first? We're doing 2 times row 2. Let's carry that out first. 2 times row 2 would just be 2 times 1, 2. Then we'd have 2 times minus 3, minus 6. Then 2 times 17, we just achieve 34. Now we're subtracting row 1. It's completely fine just to do column method and show a subtraction just like you would with regular numbers. So what we would do, we would denote that we're minusing 1, no, not 1, we'd minus 2, 1, and negative 1. What I've literally done here, I've just taken row 1 and slotted it here. And I've denoted that we're subtracting it from row 2. So what are we doing? So we do 2 minus 2, 0, minus 6 minus 1, minus 7, and then we get 34 minus 1, which would just be 34 plus 1, which is 35. Now, this will replace our new row 2. This is our new row 2. Row 2. Let me get here. It's completely fine to show you're working like this, just carrying it out step by step. What's happening first? We're timesing row 2 by 2. So we just get row 2, times it by 2, yeah? And then we're subtracting row 1, so we just take row 1 and then subtract it here. And this will give us our new row 2. The way we would write this, similar to the other ones, is just 2R2 minus R1 leads to R2. And then that's how you would write it. Now, let's move on to actually solving 2 by 2 systems of linear equations. So when we perform, in the process of row reduction, we use elementary row operations to eliminate variables from selected rows of an augmented matrix. This allows us to systematically solve the corresponding system of linear equations. To solve a 2 by 2 system of linear equations by row reduction, we aim to obtain a 1 in the top left corner and a 0 in the bottom left corner of the augmented matrix. This is equivalent to eliminating x from the corresponding equation. So when we perform this process, we may obtain one of the following forms below, that I will state here below, with corresponding numbers of solutions. So let's just say we have a 2 by 2 set of equations, and we're solving this by row reduction. So row reduction is just using row operations to simplify a solution, like we've done here with row 2. This would be row reduction, where we're simplifying a system using row operations. So if you have a system in the format of 1, 0, 1, then let's say this square here that I've drawn in here, this just represents any random number. It can be different. And let's say we have this square here, a square here. So these squares aren't necessarily the same number. I'm just using it just to denote any random number. So this could be 2, this could be 5, this could be 9, or whatever. So this just means that we have one solution. Well, obviously we know that this is the coefficient of whatever variable is here. Let's just say is 1y. Then we could just state that y is equal to this one here, right? So that means that we have one solution. However, we can obtain 0 solutions where we have something that looks like this. When we have zeros in the equation side, but we have a solution whereby 0 cannot equal that. Because obviously, if this is a random, let's say it's a random number that is an element of the real number system, this will never be equal to 0. Therefore, the equation is not satisfied. And therefore, and then, like, say, hence, no solutions, as it is not able to satisfy the equation. However, we can achieve infinitely many solutions, whereby the whole bottom row is just zeros here, and we get infinite amount of solutions. I'm going to run through a quick example with you to show this in practice using a 2 by 2 system, and I'm going to show you how to actually solve these 2 by 2 systems step by step now. Let's just say we have a question that says use elementary row operations to solve. Let's say we have an example system of y is equal to 17. Okay, so what's our first step? Augmented matrix form. So only including the coefficients. We have 2, 3, 4. Vertical line for the equals. 5, 4, 17. Now, so we have this system here. However, we need to find a solution. So the first step is to use elementary row operations. By the way, I should have stated this before. Is literally what we're talking about up here. These are all elementary row operations. It just means using row operations. It's trying to be fancy for no reason. So yeah. The augmented form. So we've got the augmented form right here. Now we're going to have to perform row reduction to try to get a solution set. How can we do that? So to find one solution, as we've seen here, we have to have a 0 in the bottom left, and then we can have a variable here. What this allows us to do, it means that we will have one variable, because this is actually 4y. This 4 is generally just 4y. If we can get it to a point where we have 4y is equal to, just say a number where 17 becomes just, where we can just say that 4y is equal to a number, right? We can easily solve this where y is just equal to n over 4. right? And we can easily solve that equation. We can't solve it, however, where we have 5x plus 4y is equal to 17. Why can't we solve this? There's two variables and one solution, one equation with a solution, so one equation. Okay, that's why we have to reduce this so there's only one variable and one solution. So it has to be one and one. You can't have two variables and one solution. It just and one equation. It just doesn't work. So how are we going to do this? Our aim is to make this 5 into a 0, therefore. So then we have one variable, one equation, and it's happy days. So how do we do this? So we start by labeling our rows, row 1, row 2. So now we have to do row 2. So how are we going to get this 5 to a 0? Well, we can make it so that this and this are the same number so they can cancel each other out. How can we do this? Well, we can multiply row 2 by 2, so we'll get 10, 8, 34. And we can multiply row 1 by 5, and so we get 10, 15, and 20. So where this is row 2, and this is row 1. So why have I done this? Well, now if you see, when we subtract these equations, we'll get 0, 8 minus 15 minus 7, 34 minus 20, 14. Wow, and look at that. This variable is now gone because 0 times by any number will just give you 0. So therefore we've cleared this and now we've only got one variable here and one equation. Okay, that's why we've done this. And a really easy way just to be able to cancel out two of these numbers is literally just to times them by each other. So we'll just times the 2 by the 5 and the 5 by the 2. And so we can get this will give us the same number, 10 and 10, and this should allow us to cancel it out. This is just if you can't find any common factors or common multiples that we can multiply into. So yeah. Now this is our new row 2. New row 2. So how would we represent this? We'll just do 2 subtract minus 5 R1. I think we're minus 5. Leads to our new R2. Whatever row you're replacing, you write that one first. This just leads to so as we're changing row 2 and we're gaining row 2 from this, we write row 2 first. Okay. Alright. Now we rewrite our augmented matrix, but now with our new row 2 here. Our new row 2 here. So what would this look like? We would have 2, 3, 4, and we'd have 0, minus 7, 14. It's important to note R1 is not changing. We're not doing anything to R1. We're simply using R1 as a tool to simplify R2. So what do we have now? We have 2, 3, 4, 0, minus 7, and 14. Well, now we have one variable, and then now it's only one equation. As this 0 means that that x value is no longer here. So now what we would do, we would convert this back into regular form. So we would have 2x, and we'd have 3y, and we'd put a plus sign here, which is equal to 4. Then we'd have 0x plus or minus 7y is equal to 14. Now we just have a set of simultaneous equations. So we have minus 7y is equal to 14. Therefore, y is equal to minus 2. And using this, we can substitute y into the first equation to get 2x plus 3 minus 2 is equal to 4. So we get 2x minus 6 is equal to 4. 2x is equal to Therefore, x is equal to 5. Alright. So, okay, so let me just summarize what I've just done there. So first step, augmented matrix. So step 1, augmented matrix. Now, step 2. Row operators, or operations rather, to reduce bottom row. It has to be the bottom row. So we have one equation, one variable. So look, if you look back over here, we have, this is our augmented matrix here, and this is me performing a row operations in order to achieve one equation, one variable. The reason I'm hammering on about this so much is because it's so important, and without this whole operation and simplifying the system of linear equations just falls apart. So it's really important that we have 1 to 1. So this is from the variable to the equation standpoint. It has to be the same number of each, otherwise it will not be able to be solved. Let's try another one. So let's try now doing a 3 by 3 system of linear equations. So we can use row operation to reduce a matrix to the form of. So now we're looking at 3 by 3 systems. 3 by 3 systems. So we can use operations to reduce the matrix to form this. So this is what we're trying to achieve when we use Gaussian elimination on a system of 3 equations and 3 solutions. Therefore, so we've got 3. So instead of there only being 2 equations, there's 3 equations and 3 unknowns. This is much more likely to come up in an IB exam. This is typically what you would get. So where we have a 1 in the top left corner, and we have the triangle of zeros, and also so we have a, this is what this has a special name. It's called row echelon form. Echelon form. And the reason we have this triangle of zeros, well, I can show you why. Because here we would have one variable, or one unknown, and look, one solution again. And then what we would do, we would find out this mystery variable and substitute it into here to get this variable as well. So again, it becomes 1 to 1. So let's just say we had, on the bottom row, we had 0, 0, 2x is equal to what? I don't know, 2, and then we had 14 here. And this is so easy to find the solution for. We just get 2x is equal to 7. Then we can use that here and just substitute it in to find all the other equations. And once we found this, well, we can substitute this into here and here, and with this solution to get this variable. So yeah, that's kind of the theory behind it and why we do what we do. It just literally just helps us easily solve these systems of equations. Okay, so now I'm going to show you different formats of the matrix and how many solutions this would give you. If it gives you a unique solution, no solutions, infinite solutions. Okay, so if you reduce the matrix to the form of 1, 0, 0, 0, 1. this system has a unique solution. So okay. However, when we're aiming to reduce our matrix, we might come across the following forms, such as this: 1, 0, 0, 0, 1. Where the squares are non-zero numbers. So obviously, if you have a full row of zeros, zero cannot equal a non-zero number. It's just not possible, and the equations are just therefore unsatisfied, and therefore it's absurd. So yeah, that's what you would write. You typically write, it says that zero is equal to, so like the system suggests that, say we did get this solution set, yeah, say we did get this, we'll just write zero. The system states zero is equal to, let's just say this is just a random non-zero number, and then you write which is absurd. That's typically how we would comment on the solution. And in these cases, we would say that there is no solution and that the system is inconsistent. However, we might find one of these forms. So if we have 0, 0, so you should see if there's 4 zeros on the bottom row, then that just literally means that there's infinitely many solutions. So yeah, we can express these solutions in terms of parameters such as s and t. I'll go through this later. This will come later. I'll do a couple questions on this, showing you exactly what I mean. It's okay if you don't get it right now. I'll go through a couple examples and I'll show you exactly how to attack them. So let's look at our first question, shall we? So we have this system of linear equations: x plus 3y minus z is equal to 15, 2x plus y plus z is equal to 7, x minus y minus 2z is equal to 0. The approach is the exact same as a 2 by 2 system of equations. Nothing really changes except for we have one extra column and row to deal with. So yeah, what we do first, of course, augmented matrix form. Step 1. Step 1. AU augmented matrix. It just means augmented matrix form. So what we're going to be doing here is obviously converting this to augmented matrix form. Don't get scared of the extra variable. It's the exact same. You only take the coefficients, ignoring the addition signs and the equal sign, replacing it with obviously a vertical line, and removing all of the variables from the equations. So how would we do this? Taking only the coefficients, remember? We'd have 1 plus 3. I say that again. We don't write plus in the thing. It's just a natural instinct. So 2, 1. It's okay if you write plus, just remember just to rub it out. 1 minus 1 minus 2. And then we have 0. That's our first. So now we're in augmented matrix form. Now remember what we're trying to achieve here. We're trying to get the 3 zeros in the bottom left, okay? The ones, yeah, they're helpful, but it doesn't really matter. The ones don't matter nearly as much as having these 3 zeros. You can still solve it with these not being ones. It's just easier, and you can solve it just by looking at it when they're ones. But this triangle of zeros, this is so important, it's ridiculous. So we need to find this. So how are we going to do this? Okay, so firstly, I'm going to state that usually one of the rows stays the same. This is typically row 1, and that's the row we're using to manipulate both of the other two rows. So this is row 1, this is row 2, and this is row 3. Now, remember, we're trying to obtain these leftmost zeros. So what we typically do, right, we try to achieve these two zeros. So the ones in, wait, let me just write this out real quick. Sorry. And that's not a zero, that's just pretend they're the squares. Square here. Okay, so this is how we go for it. So the first zero we try to find, this one here. Second zero is this one here. Then we use this equation, this one, to find this zero. I'll show you how we do it. So, okay. So what do we first try to do? We try to make this a zero. How do we do that? Well, we have to make this and this the same number so we can cancel them out when we add or subtract the equations. So we have 1 and 2 here. So row 2, remember, the row that you're changing, you put at the top, 2, 1, 1, 7. And then this row, what do we have to do to 1 to make it 2? Well, we multiply it by 2, don't we? Say this number was, like, say this 1 was like at 3, for example. Just so I can show you. To make 3, well, we can't make 3 into 2, and we can't make 2 into 3. Well, in this case, we just multiply 3 by 2, and 2 by 3, so they're both 6's now, and we can cancel them out. But in this case, it is 1, which is quite fortunate. So we just write out row 2, just like so, in this case, and we have row 1. Row 1, we multiply by 2 to get this 2 on the left here, so we get 2, 6, minus 2, and then we get then we just get 30. Now, how can we cancel out these 2's? Well, we can just subtract the equations. So 2 minus 2, 0. 1 minus 6, that'll give you minus 5. 1 minus minus 2, which is 1 plus 2, and we get 3. Then we get 7 minus 30, which is minus 23. And this is our new row 2. And would you look at that? We have one of our 3 zeros. So this is our new row 2. We won't rewrite our augmented matrix yet, because we're going to try to change this into a 0 as well. So let's say, okay, so row 3, that's the row we're changing now to get this 1 as a 0. So row 3 at the top, you guys know the score by now. 1 minus 1 minus 2, 0. So lucky us, these two numbers are already matching, so we can easily cancel them out. So we can just write row 1 without having to multiply by anything. So we have 1, 3, 1, and negative 15. Oh wait, no, we just have 15 here, sorry. Yep, that seems about right. We have a negative 1 there. 1, 2, okay. So how do we cancel out the 1's? Well, we just subtract the equations once again. 1 minus 1, you get 0. Minus 1 minus 3, you just get minus 4. Minus 2 minus minus 1, that's just minus 2 plus 1, so we get minus 1. 0 minus 15, you get minus 15. Now, if you look here, wow, look at that, we've got another 0. And this is our new row 3. Now what we can do, we can use our new row 2 and new row 3. Now we can rewrite our augmented matrix. Remember, row 1 has not changed. We've only been using row 1 to manipulate row 2 and row 3. So we have row 1 as 3 minus 1, 15. I think row 2 was, yeah, 0 minus 5, 3 minus 23. Yeah, there we go. We have 0 minus 4 minus 1 minus 15. So now we have our two zeros. We need this number here to be a 0 as well. Okay, so how are we going to do this? See, this is the reason why having these two zeros is so important, because you can now change this into a 0 without the numbers here interfering and, yeah, it becoming just a big mess, really. So it's really helpful that these two are 0. that we can easily manipulate it so that this can be a 0 as well. If there were numbers, then we would have to balance out the numbers as well, making this a 0. So yeah, that's the reasoning behind that. So how are you going to make -4 and 5 the same number? Well, I can just multiply them by each other. So I can just do -5 times by -4 and -4 times by -5. So how would we do this? So what is the row we're manipulating? Row 3. That's what we're trying to replace. So we write that one above. But we're going to be multiplying it by -5. So we get 0, 20, 5, and then we get 75 as well. 75 as well. Okay. If you want, we can just multiply row 4 by 5 and then row 5 by 4 instead of multiplying them by -4 and -5. Okay, so I'm just going to times them by 4 and 5. Why have I done this? So that they're going to be the same number and we can easily cancel them out. So row 3, when we're changing, so 0 times by 5 is still 0. 5 times by -4, -20. 5 times by -1, we just get -5. We get 5 times by -75. -15, we just get 75, sorry, -75. Here we do 4 times by 0, which is 0. 4 times by -5, -20. 4 times by 3, 12. 4 times by 23, we get 92, I believe. So now what do we do? Well, to make this column a 0, what do? We add the equations. I mean, no, we would subtract the equations because a minus a minus would give you a positive. So a negative, subtract a negative gives you a positive. So we will have 0, 20 -20 minus -20 would give you 0 as well. Because we're just adding 20 to -20. -5 minus 12, we get -17. -75 minus -92, we will get 17. 17 there. Alright, so this is meant to be a -92, sorry, I missed out the negative here. I just remembered it's -75 minus 92. And this is -75 plus 92, and you get 17. Sorry about that, I just realised that. The hardest part about this is literally just maintaining all the negatives. As long as you have them, then you'll be fine. So, now we can write out our new augmented matrix. So, remember, row 2 is not changing here. We're only using row 2 to manipulate row 3. Because as we've seen, wait, there we go. So this is our new row 3. So what would this look like? So we have 1, 3, -1, 15, 0, -5, 3, -23. And we have 0, 0, -17, 17. Do not write the changed version of this row where we've multiplied it by 4. Don't do that. You have to keep it consistent with the system. And as we've only multiplied it by 4 in that case to manipulate the system. That's the only reason why we multiplied it by 4. We keep it the same. Except, however, this row 3, the one we were manipulating, is in its new form here, which we've plugged in. So now what we can do, we can write out our systems of equations. So we have x plus 3y minus z is equal to 15. We have 0 plus 0x plus minus 5y plus 3z is equal to minus 23. Then we have minus 17y, z I mean, is equal to 17. Well, now we know that z is equal to -1. So, using this, we can just substitute z is equal to -1 into this equation. And So why are we not substituting z equals -1 into this equation? Well, because then we'll have two unknowns, these two, and one solution, and one equation, which we cannot have. So we substitute it into here, where there's this 0 means that this is no longer part of the equation. This, and we only have one variable, one equation. So what would this be? So we'd literally just it's like how we're solving a simultaneous equation. We'll just substitute the -1 in, so we get 5 minus 5y plus 3 minus 1 minus 1, negative 23. Now we'd have minus 5y minus 3 is equal to negative 23. We get minus 5y is equal to 20 minus 20, and y is equal to 4. Now, using z and y, we can substitute it into the first equation to find x. So we get x plus 3 times by 4, where the y gets substituted in, minus 1, this is the z, where the z gets substituted in, is equal to 15. So we have x plus 12 plus 1 is equal to 15. So we have x plus 13 equal to 15. Then we have x is equal to 2. Hopefully now this explains why it's important to have these three zeros, so that we can easily find out our solutions with following all the rules. And yeah, let's try a different example now. We look for a slightly harder question for us to do. Okay, let's see here we have this system here. So solve using row operations. X plus 2y plus z is equal to 3. 2x minus y plus z is equal to 8. 3x minus 4y plus z is equal to 18. Now, what's our first step? Augmented matrix. Only coefficients, leave out all the variables, the plus signs, and replace the equal signs with a vertical line. So for this one it'll be 1, then 2, 1, vertical line, 3. 2, minus 1, 1, 8. 3, minus 4, 1, 18. I've literally just dragged the coefficients from these equations. Now label our rows. So row 1, row 2, row 3. If you don't get confused and you remember that we label it going down accordingly, then you don't have to write this all down. So how do we solve this? So again, we're going to be trying to achieve the 3 zeros in the bottom left, where the priority is this one first, this one second, and then lastly this one. So let's do it. So we have row 1, row 2, row 3. So we're trying to get this 0 in the leftmost column of row 2. How do we do this? So firstly, we have row 2 and row 1. So what can we do to row 1 to get row 2? To get a 2 in the leftmost column, how can we make this 1 into a 2? Well, we can just multiply it by 2. So by multiplying this 1 here by 2, we have to multiply the entirety of this equation by 2, so that we can get the same solutions. Otherwise, it will be all messed up and you won't get the same solutions. So let's do that now. Remember, row 2 is the one that we're changing, so we write it at the top of the subtraction, and we'd have multiplying row 2 by row 1 by 2, so we'd get 2, 4, 2, 6. And then now, how can we cancel out the 2's in the left here? Well, we can just subtract the equations, and we get 0, minus 1, minus 4, let's get minus 5, 1, minus 2, get negative 1, then we get 8, minus 6, and then 8 minus 6, which we just get 2. don't know why I said minus minus, let's just 8 minus 6, and then we get 2. Alright, so this is our new row 2. Okay, so now what's the next zero we have to get? This one here. The bottom left, so the leftmost column of row 3. Alright, how can we do this? Well, this is our new row 2, so we can use row 1 again, because it's remained unchanged, because we've only manipulated row 2. We've only used row 1 to manipulate row 2, without changing row 1. We've only changed row 2. So, we can use row 1 again to cancel out and obtain a 0 in the here, right here. How can we do this? Well, again, we look at how can we make the 1 into a 3? Well, we just multiply the top row by 3. So, doing this now. So, row 3 is the one we're manipulating, so we write it on the top. 3 minus 4, 1, 18. And then we write out our other one, which would be so we're multiplying row 1 by 3. So this row here by 3. So we get 3, 3, 6, 1, 3, 6, 3, and then 9. Okay, so how can we achieve a 0 here? Well, we can just subtract the two equations again. So we get 0, minus 4, minus 6, minus 10, minus 2, and now 9. Well, see now this is our new R3. Now we can create our new augmented matrix using the new R2 and the new R3, but where R1 has simply just stayed the same, as we've only used it to manipulate row 3 and row 2, not switch out row 1 with what we've gone. We're only switching out row 2 and row 3 with the respective values we've obtained from using row 1. So our new augmented matrix will look like this. 1, 2, 1, 3. 0, minus 5, minus 1, 2. 0, minus 10, minus 2, 9. Alright, so now we have our 3 zeros here. The last 0 we actually have to get is this one here. The reason it's the last one is because we need these 2 zeros to be able to successfully get this 0. So, now what do we do? So we have 0, 0, and we need to make this negative 10 into a 0. How do we do this? How do we make minus 5 into, or make the 5 into a 10? Well, we just multiply it by 2. So what we do, in effect, we have row 2 and we multiply it by 2. So what would that look like? So row 3 is the one we're actually changing. So we have 0, minus 10, minus 2, and 9. Now we just do 2 times by row 2, which we get 0, minus 10, minus 2, and 4. Now, why have we multiplied the top row by 2, or I mean row 2 by 2? Well, it's to make it so this 5 matches a 10, so we can easily just cancel each one out. So what does this look like? So this is our row 3. This is 5R2. Okay, so what do we do now? To cancel out these two negative 10s, we can just subtract them, because a minusing a negative number will just get you adding the number. So we would have 0. Minus 10 minus 10, we just get 0. Minus 2 minus 2, we just get 0 again. And then we get 9 minus 4, and we have 5. You may have noticed what's wrong with this system, and you may see it when we finally write our augmented matrix now. We have our new augmented matrix using this new row 3. Remember, row 2 is now still the same. Just like row 1, we've only used it to manipulate another row, so therefore it stays the same. So we have 1, 2, 1, 3. Then we have 0, minus 5, minus 1, 2. And on the right here, we just have 0, 0, 0, 5. So basically, what this system is now stating, if you take it back to normal form, what does it look like in normal form? We have these three sets of equations. Plus 2y plus z is equal to 3. 0 minus 5y minus z is equal to 2. 0x plus 0y plus 0z is equal to 5. So basically what this system is stating is that 0x plus 0y plus 0z is equal to 5, which we know that this is absurd, as 0 cannot equal 5. This is what you'd have to write in an exam. Typically you'd write absurd, or this solution is invalid, or something along those lines, or we can reject this solution, meaning that there is no solution. So therefore there is no solution, and the system is therefore inconsistent. Right, so now that we've completed this one, let's try another example. Alright, let's do this question here. Inconsistency just literally just means that there are not enough variables for the number of equations. So here we just have 0 variables, as they all get multiplied by 0 and therefore get cancelled, and one equation with a solution. Alright, let's try this one now. If you feel free to pause and actually have a go, and if you get stuck, then you can obviously rewind the video, forward it, whatever you want, just jump around and the video, and yeah. I do hope that this is okay and quite effective. I'm going to try to minimize the amount of editing that I do to keep it as natural as possible, to show all the working out and the real thought process behind each one. So this system, step 1, obviously, augmented matrix. How would you write this in augmented matrix? Well, we'll just simply write all the coefficients, leaving out the variables, replacing the equal sign with the vertical line, and removing all the addition sign. So what would this look like? 2 minus 1, 1, 5, vertical line here, 1, 1, minus 1, 2, 3, minus 3, 3, 8. Okay. So once again, we're going to achieve these 3 zeros. It doesn't really matter which order you do these two in. However, you have to get these two before getting our last one, which is this one here. Okay. So what would this look like? So let's say we're going to try obtain this 0 first, which is the leftmost 0 of R2. So what would this look like? Basically, we would have to make it so that these two numbers match, so we can cancel it out and get a 0 in this position here. So what can we do to 1 to make it a 2? Well, we just multiply it by 2. So in this case, we'll be multiplying R2 by 2. And remember, the equation that we are replacing, the equation or row that we are replacing is the one that we put on top. So we put 2, so we put, right, 2, 2, minus 2. Then we have a 4 here. Now what do we have? Now we write row 1, which is 2, minus 1, 1, 5. So what do we do here? We subtract these equations to get a 0 in this left column. So how do we do this? So we just do 2 minus 2, 0. 2 minus 1, we get 3. Minus 2 minus 1, we get minus 3. 4 minus 5, we get minus 1. This is our new R2. Now what we do next is we're trying to get our 0 here, which is in the leftmost column of R3. So left column of R3. So what do we do here? So we have R3 here. We rub out this so we just have a clear understanding of what we have. So this is R3. This is R1. So we're going to be using R1 again. You'll typically see that we're only going to be using R1 to find these two zeros. It's just easier that way. I find that's just the most efficient method. You can use other rows, but it does get a bit messy, especially if you do have negatives. It can get extremely confusing. So I just like to keep one row constant, which is row 1, and the other two, which I'm having to manipulate, row 2 and row 3, those are the ones that I only change. So we have to make this 3 and this 2 match so we can get this 0 in the bottom left, right? This 0 here in the bottom left. So what can we do? Well, we can look for common multiples, but the quickest way, if you don't want to start writing everything out, I know these two is quite easy, but if you don't want to start writing it out, well, we can just multiply them by each other. So 2 times 3 and 3 times 2. This is a guaranteed method to get the same number, and it's quite frankly the quickest and easiest method. So we're going to be multiplying row 1 by 3 and row 3 by 2. So what does it look like? Row 3, remember, at the top, because that's the one we are we're changing. So row 3, this one here. So we're multiplying it by 2. So 3 times 2, 6. 2 times minus 3, minus 6. And then we have 6 here. We have 16 here. Now we have row 1. What do we do with row 1? Well, we're going to be what we're going to be doing. We're going to be multiplying it by 3. So we get 6 minus 3. Minus 2, sorry. No, it is minus 3. Going mad. Minus 3. And then we have 3 here. Yep, 3 here. And we have 15. Okay, so what can we do to this leftmost column to get a 0 here? Well, we can subtract both equations because 6 minus 6 is 0. So we get minus 6 minus minus 3 to get negative 3. 6 minus 3, so we can get 3. 16 minus 15, we'll get 1. So this is our new R3. 3. So now let's write out our new augmented matrix, including both R2 and R3. So we will have 2 minus 1, 1, 5. Our new R2, which would be our 0, 3, minus 3, 1. And then we have our 0, minus 3, 3, 1, which is our new R3. So we have R1, R2, R3. Okay, so if you remember, we have to have our triangle of zeros, where this is the first column, second column, and then we just don't really care about the third, and then the solution, we don't really care. So what we do here, to get this second 0, we're going to be using row 2 and row 3. It is imperative that you use the row 2 and row 3, the ones that you have the zeros in, so that we can make this into a 0 without changing this. Because no matter what we do to this, no matter what we multiply these by, they will remain 0. And when we add them and subtract them eventually to get this row to 0, they won't change. So what we do here now is we take row 1 and row 3. Lucky for us, these two are matching. They're both 3s, right? Regardless if this is a negative, it doesn't matter. They're both 3s, so that means that we can easily just cancel them out. So how would we do this? Since row 3 is the one that we're changing, we have 0, minus 3, 3, 1. Then we have 0, 3, minus 3, minus 1. The reason I'm not changing row 2 here, or multiplying it by anything, because the numbers are already matching. We don't have to do anything. So what do? We have 0 and 0, so no matter what we do, they will stay the same. So how do we cancel out the negative 3 and the 3? Well, minus 3 plus 3 will give you 0, so we would have to add these two equations. So we have 0, 0, 3 plus minus 3, just 3 minus 3, which we get 0. 1 minus plus minus 1, we get 0 again. See, I think you guys will notice what's unique about this bottom line here. So now let's write our augmented matrix. So we have 2 minus 1, 1, 5 stays the same because we haven't swapped it out with anything. 0, 1, minus 1. I mean, not minus 1, sorry. 0, 0, 3, minus 1. Then we have 0, 0, 0 as our new R3. As you can see, that the R2 hasn't changed from completing this addition, as that's not the one we were aiming to manipulate. I mean, the R2 is this one, sorry. The R2, this R2 here has not changed. So, if you remember before, this full line of zeros just means that there are infinitely many solutions. Then you can write in brackets indicated by row 3. Okay, so how are we going to tackle this? Well, we can set one of the variables equal to a certain letter or whatever you want. So in this case, we can say that we can set that z, we can say that z is equal to t. Now, if you remember that this is the x column, y and z, this is the solutions, right? So we can write this all in the expanded form if you wish. So this will just be 2x minus y plus z. So now we can just set z into z as a parameter or just any variables. So t, let's just say we're using t. Now we can use row 2 now because we can't use row 3 because we'll just obtain a 0. So we can substitute z is equal to t into row 2. So what is row 2? Firstly, is 3y minus 3z is equal to minus 1. Well, so using z is equal to t, we can find that 3y is equal to 3y minus 3t is equal to minus 1. So therefore 3y is equal to 3t minus 1. And then dividing both sides by 3, we obtain that y is equal to t minus a third. Right. So now we have y is equal to t equal to a third and z is equal to t. We can now solve for x using the first row here. So writing the first row in expanded form, we get 2x minus y plus 1 equal to 5. Plus z, sorry. The coefficient of z is 1. So yeah. Now we can substitute these values here. Just pretend like it's a normal substitution. It doesn't matter about the t, the minus 3, or the minus the third. It's the same thing. It's the same process. We're just substituting them in, these expressions in. So we get 2x minus t minus the third plus t equal to 5. So we get 2x minus t plus a third plus t is equal to 5. These t's cancel out. The reason why this minus a third is now a positive a third is because we just pretended there's a minus 1 here. Minus 1 times t, we get that. Minus 1 times by a third, positive a third. So we just have minus t plus a third. We can cancel these two out because t minus t is 0, and we have 2x plus third, which is equal to 5. Now, what do? We can do 2x is equal to 5 minus a third. So this gives you 2x is equal to, if you can't work it out, it's 14 over 3, but how I've done it is I just converted this into thirds, so you get minus a third. 15 over 3, and you get 14 over 3, so 2x, and then we get x is hence equal to 14 over 3 divided by 2, which is just 14 over 3 times by a half, and we just get 14 over 6, or 7 over 3. Now, we have the solutions Now we can state that although they have infinitely many solutions, the solution set has to be of the form, or has the form. So the solutions have the form x is equal to 7 over 3, y is equal to t minus a third, z is equal to t, whereby it's common to is imperatively state that t is an element of the real number system. And that's how you solve it, where t can be seen as a parameter. You could use s, t. We typically use s or t for this. So it's not sufficient just to say that it has infinitely many solution indicated by row 3. Yes, this is helpful, but it's even more helpful to go out and find the form in which the solutions will be in. Because this is typical, what would happen in an IB exam. You would actually have to find the form of the solution. So you would have to find these, that z is equal to t, x equal to 7 over 3. Just a form of solution. You won't have to, because it's infinite, you can't possibly find all solutions, but you can state the form of the solutions. Now, let's try another question. So, now we have the system, let's just say that it's x minus z equal to minus 1, 2x plus y plus 3z equal to 13. Let's just say x plus 8y plus 9z equal to, let's just say, random variable a, where a is an element of the real number system. So this will mimic the format of some IB questions. So we can just say that the first question will most likely be use row operations to reduce the system to row echelon form. So what does that mean? That's when we have our triangle of zeros in the bottom left. So yeah. So let's go ahead and do that. So what's the first step? Augmented matrix every time. 1, minus 2, minus 1, minus 1 here. 2, 1, 3, 13. Then we have 1, 8, 9. And we just have an A here. Right, lovely. So remember, 3 zeros. This one first, second, and third. So how do we do this? So what can we do to 1 to make it like 2, make it equal to 2, so that we can cancel these out and get it to 0? Well, we can just multiply 1 by 2. So doing this, we write out row 2 first. We're doing nothing by row 1, but it's times it by 1. So we just have 2, 1, 3, 13. And then we have, sorry, I just check. Then we have 2 minus 4 minus 2 minus 2. Then how can we make it so this column is 0 to get this 0 here? Well, we just subtract the equations to get 0, 1 minus minus 4, 5, 3 minus minus 2, 5 again. And then we get 13 minus minus 2, 15 here. 15. Nice, lovely. So this is our new row 2. So first 0, check, done. Now our second 0. This is for row 3. So we have to make this number here 0. How do we do this? Well, we can see, lucky for us, these numbers here are already matching. So what we can do now is literally just write them out now. So what's the row we're changing? Row 3. So that's the one we write first. So we have 1, 1, 8, 9, then A. This is row 3, the one that we're changing. Then we have row 1, which is just 1, negative 2, negative 1, negative 1. Alright, so how do we obtain a 0 on the left hand side here? So what we can subtract both equations. Because 1 minus 1 will just give you 0. 8 minus 2 will just give you 10. Then 9 minus minus 1, we get 10 as well. Then here, okay, here, don't be afraid of the variable. You just write it how it is. So what are we doing here? A minus minus 1. What is that? A plus 1. So just write A plus 1. There we go. It's really simple as that. So now we have our new R3. 3. Alright. So let's write out our new augmented matrix using our new R2 and a new R3. But of course, leave R1 the same. Okay. So we have 1 minus 2 minus 1 minus 1 0 5 5 15. And here we have 0 10 10 A plus 1. Okay, what do we do here? So now we're going to find our third 0. So we found this 0. Nicely done. Now we have this 0 to find here. So how are we going to do this? So this is the second column of the third row. So what's that? That's this one here. How do we do this? So how do we make a 5 match with the 10? Well, what we can do is multiply the 5 by 2, and we can keep the 10 the same, because the 5 can become a 10 easily without the 10 having to be multiplied with anything. So we just get, so writing out row 3 first, because that's the one we're going to be changing with what we obtain. So we get A plus 1. Then multiplying row 2 by 2, we get 0, 10, 10, 30. I can't state how important it is to do it to the entirety of the equation. If you multiply one thing, you have to multiply the entire equation. So then we get, so how can we obtain 0 from 10 and 10? Well, we can subtract them. So we subtract both equations. So we have 0, 0, 0, A plus 1, A plus 1 minus 30. Well, we can just do, that will just literally just be A minus 29 right here. So now, of course, you guys can probably see from the bottom column that it's going to have no solutions, but let's just write down the finished matrix for just completion's sake. So we'd have 1 minus 2 minus 1 minus 1. Our row 2 is going to stay the same here, because we only use it to manipulate row 3. So it stays the same from once we've changed it from row 1. So we have 0, 5, 5, 15. And then we have 0, 0, 0, A minus 29. Okay, so using row 3, indicated by row 3, the system will have no solutions if A does not equal 29. Why? Okay, because if A is equal to 29, we have 29 minus 29, which is just 0, so we just have 0 is equal to 0, which is a valid solution. So the system will have no solutions if 0 is not 29, because if 0 is not 29, 0 cannot equal whatever A minus 29 is, where A does not equal 29. Okay, because then the equation won't be satisfied, because 0 won't be equal to 0, and whatever number A minus 29 produces will not be equal to 0, so therefore have no solutions, right? However, we can now look at the next question, which is, under what conditions does the system have infinitely many solutions? Find the solutions in this case. So typically in the IB exam, this is what would happen. It would be a multi-step equation where the first would ask you to reduce the system to row echelon form, which we've done here. As we can see, 3 zeros, there's a triangle of zeros here. And then the next step is to find the value of A, which the system has no solutions. And under what conditions does the system have infinitely many solutions? Find the solutions in this case. So what we can do here is do what we did before when the system had infinitely many solutions, where let's say, so where does it, so firstly we have to find a value of a where it will have infinitely many solutions. So that would be where a minus 29 is equal to 0, because then we'd have a full row of zeros on the bottom, and we just have, so a has to be equal to 29 for this to be possible firstly. So rewriting the whole of the augmented matrix would have 1 minus 2 1 minus 1. Okay, firstly, alright, wait, let me just rub all of this out. To state that it's in row echelon form, we need to remember that we have to have ones going across here. So this needs to be a 1, this needs to be a 1, and this needs to be 1, as we've seen before. So this in row echelon form would just literally be this system. And what would we do? So how can we make this 5 into a 1? Well, we can just take a fifth of this entire row. So we'd have, so what would it be? So we'd have, taking a fifth of this, a fifth of 5 is just 1. A fifth of 5 again is just 1. And a fifth of 15 is just 3. Now, what do we do so we've done that to row 2. So now we've gotten our 1s, which are here. We've got all our 1s here. We can't get a 1 here because obviously there's a 0 here, as we've seen. This will be the answer to like A, where it would be for row echelon form. You would need to get these two 1s at the very least. If this is not possible, then we can leave it. But here we saw I can just take a fifth of this row and get this 1 here. So that is important. So let's now say, so going back to where we have infinitely many solutions, A has to be equal to 29 to get this form. Okay, so now we're rewriting our augmented matrix. So we'd have minus 1 here. Now we would have, what would we have? We would have 0, 1, 1, 3, using our row echelon format that we use, 0, 0, and then A minus 29. Where we stated that A is 29, so then we have 29 minus 29, where we know is 0. Now, it's the same approach as the last example we saw when we had infinitely many solutions, where we can just set z to any variable. I'd like to set it to t. That's what we usually use, so we say z is equal to t. Now, using row 2, obviously, can't use row 3 again, just like in the last example, because we will just obtain 0, and we won't get anywhere. So using z is equal to t, we actually get y plus z is equal to 3. So, but here z is equal to t, so we get y plus t is equal to 3. And for y is equal to 3 minus t. Now, using z is equal to t and y is equal to 3 minus t, we can find x in this equation here. How can we do that? We can just show this with the augmented matrix form, and we can revert it back into the expanded form where you have x minus 2y minus 2 minus z is equal to minus 1. If you're wondering where I'm getting these variables from, as we saw before, this was the x column, this was the y column, this was the z, and this was the solutions. Okay? And I just literally just slot the y's and z's back in, because these are the coefficients of these variables. So I can just slot the x, y, and z back in. So now using z is equal to t and y is equal to 3 minus t, what we can do is x is minus, minus 2 times by 3 minus t, substituting this for y. Then we have z is equal to t, so we can substitute t for z, so minus t is equal to minus 1. So what do we do? X, so we do expand the brackets, so minus 2 times by 3, minus 6, minus 2 times by minus t is plus 2t. and we have a minus t here, so minus t is equal to minus 1. What do we do in this case? So we have x combined like terms. So x plus t is equal to, so we add the 1 over. So we have add the 6 over. So we get minus 1 plus 6, which will just give you minus 5. And then what we do achieve is therefore x is equal to wait, this is a minus 1 and we've added 6 to it, so it would be a 5 here. Sorry about that. And so we have x plus t is equal to 5. We just take away the t. So now we can write that therefore where infinite a is equal to 29, whereby solutions will have the form of x is equal to 5 minus t, y is equal to 3 minus t, and z is equal to t, where t is an element of the real number system. You can write it like in its like little bold form if you really want to, but just putting like a line through it will suffice. Alright, so I think that's going to be it for this video. Please in the comments just give any advice and whatever. I'll reiterate, I'll try to make sure that this remains as unedited as possible, so we minimize the editing so we can show the full walkthrough for each question. Please in the comments give any advice, any improvements, that would be greatly appreciated. Thank you.